So let's start with relativity. So this morning we're going to have a relativity lecture and a quantum lecture. So we'll start with relativity lecture. And the first thing in the relativity lecture is the concept of a space-time diagram. So these sorts of diagrams are extremely important in the context of understanding Einstein's ideas about relativity. Okay, so that'll be the first topic. Now, I'd like to start by saying a little bit about Newton's ideas about space and time. So some of you may have heard this before, and I will explain what this terminology means. So in Newton's mind, he had the idea that space is absolute and time is absolute. So I'll just write that down and then talk about that. Okay, so what does that exactly mean? Well, I have a copy of Newton's Principia Mathematica here. This is one of the most influential books in the history of humanity. Do any of you have this book? It's a great book. It's a fantastic book. Just to read, I mean, Newton was a genius, and just to read his words and get a sense of what people were thinking back then, and the huge leap in understanding that he made. It's really, really cool to actually read the original, Newton's original words. So, in fact, here I have Newton's original words, actually. So let's see what he has to say about this absolute space. Okay, so to quote from Newton, he says, "Absolute space, of its own nature, without reference to anything external, always remains homogeneous and immovable." Okay, and then there's blah, 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 blah. And then a little bit later he says, "For example, if the Earth moves, the space of our air, which in a relative sense and with respect to the Earth always remains the same," so the air remains at rest with respect to the Earth, okay, "will now be one part of the absolute space into which the air passes, now another part of it, and thus will be changing continually in an absolute sense." Okay, so what does all that mean? Okay, so what that means is just something like this. So Newton had the idea that there's this absolute space in the sense that suppose that this is the Earth, and the Earth is located somewhere in this absolute space, which is the blackboard. Then as the Earth moves, say in its orbit around the sun, then the Earth is at one time occupying this volume of that absolute space, and later on, it's occupying a different volume of that absolute space. Okay, and so objects occupy different volumes of that absolute space as they move around. Okay, so there's this sense of an absolute rest. A space in which something could be absolutely at rest. And Newton says in here that we can't actually determine, like it's not necessarily true that any particular object in the universe is at rest. But typically in our minds, we have the idea that maybe the sun is at rest with respect to that absolute space. And then since the Earth moves around the sun, then the Earth is in motion in that absolute space. Okay? So let me draw a picture here. So here is the surface of the Earth, and we will set up a coordinate system, say horizontal coordinate x, vertical coordinate y, and we could have some things happening in this space. So we could have a person standing over here at rest in that space, or at rest in that coordinate system, but this is the surface of the Earth here, and the Earth is in motion around the sun, and so this person is, say, moving through Newton's absolute space. First occupying this location of that space, then this location, and so on. Okay. If this person, say, throws a baseball, that baseball will travel on some trajectory like this, and it will have a different motion through that absolute space than that person. Okay. There's also this notion of absolute time. So let's read what Newton has to say here. So he says that absolute, true, and mathematical time, in and of itself, and of its own nature, without reference to anything external, flows uniformly, and by another name is called duration. Okay, so what does that mean? So that means something like this. That means that somehow in the universe, there's this sort of great big grandfather clock up in the sky, okay, and time moves when 1 second elapses for that universal clock, then 1 second elapses for everyone else, okay, regardless of their state of motion or their position or anything like that. Okay, so here is a person here, and they have a watch, tick, 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 tick. And suppose that we strap a wristwatch to that baseball. Well, that wristwatch, as this baseball is moving, that wristwatch is ticking away time. Okay, and so Newton's idea of universal time is that when 1 second elapses for that universal clock, that absolute clock, 1 second has elapsed for the universe. That means 1 second will have elapsed on this clock, and 1 second will have elapsed on that clock, regardless of the state of motion of this clock relative to that clock, and so on and so forth. Okay, so for Newton, space and time were both absolute. They were this sort of fixed things, these rigid things. Okay, but there's certain problems with that. And Einstein came along, and he said, well, that's not quite right. That's not right at all. In fact, these two ideas are, those two ideas of absolute space, absolute time, they're wrong. Okay, and we're going to, in the process of these few lectures on relativity, we're going to discover exactly how they're wrong and, in fact, what is correct. Okay, so Einstein said that space and time themselves are not absolute, but they are relative. Okay, so basically that means that time, for example, time depends upon the motion of the observer. Okay, so here's an example. So you've got a watch, and I've got a watch, and suppose they're identical watches, and we synchronize them, and they're both reading exactly, say, 12 noon. Okay, and then I go for, say, a walk around the building, and I come back. We put our watches next to each other again, and we find that, yes, they're in sync. They're both ticking at the same rate. But we will find that less time has elapsed for me. My clock is behind your clock. Okay, they were originally both reading exactly the same time and ticking in sync with each other. I go around a walk around the block. I come back. I find that they're both now ticking at the same rate again, but my clock is behind. Less time has elapsed for me, okay, relative to your clock. Okay, so this is a fact about our universe, which we're going to try to understand. Okay, so basically, the first step in trying to understand how time and space are relative and what exactly that means is to explicitly show the motion of objects not only in space, like in this diagram, but also in time. Okay, so let me just write that down, and I'll give you a diagram. Okay. So basically, any object, the key point here is that any object, regardless of its state of motion through space, is inexorably moving forward through time. Okay, so this object here, while it's not, here it's moving in space, now it's moving in space, now it's not, now it's just sitting there. It's not moving through space, and yet it's still moving through time. If I strap a wristwatch to that thing, time will be ticking for that object. Okay, even though I'm at rest, my clock is still ticking. I'm moving forward in time. Okay, so what we need to do is to show an object's motion not only through space, but also explicitly show its motion through time. Okay, and that's a space-time diagram. So let me give you an example here, a couple of examples. Okay, so let's suppose that this is Alice, and we're going to take the point of view here that Alice is just at rest. Okay, so that's like me just standing here like this. Okay, and Alice has an x-axis, okay, so that's in, say, in that direction to the right. And things can move along her x-axis back and forth. So let's draw her x-axis. So this is space according to Alice. So that's her x-axis, the x-axis according to Alice. So we put a subscript A on it. That's space according to Alice. And things can be happening in this space. Okay, so for example, there could be, say, Bob. Bob is standing beside Alice at rest. So here's Alice, and here's Bob, just standing there at rest. Okay. Other things could be happening. Okay. Suppose we have someone over here, say Cleopatra, who is running with some speed v. So running along Alice's x-axis. So in motion in Alice's space. Okay, or we could have people, other people, and so on and so forth. Okay, so now this is showing their motion in space. This one is not in motion in Alice's space. This one is in motion in Alice's space. That's fine, but we also need to show the motion through time. Okay, so the simplest person for whom to show that is Alice herself. So Alice is at rest in her space, but she's moving forward in time. Her clock is ticking, 1, 2, 3, 4. She's aging. Okay, so she's moving forward in time. How do you think we could represent that? Yeah. Vertical line. Perfect. Okay, so I'm going to take this diagram showing motion only in space and convert it into a space-time diagram. So there's the space part of the space-time diagram. And here's the time part, just a vertical line. Okay, so in this vertical line here, what we could say is this is Alice, right? This point here is Alice at this location, say x equals xa equals 0. Let's say her position is 0 here. So this is Alice when her clock reads 0. Okay, this is Alice when her clock reads 1. This is Alice when her clock reads 2, 3, 4, and so on. Okay, so this is a picture. This is a space-time picture of Alice standing at rest. So as time goes on, her position in space doesn't change. It always remains 0, but her time nevertheless ticks away. Okay, so this is time according to Alice. Okay, there will be time according to Bob and so on and so forth. This is Bob over here. Okay, so this is called a world line. This is a picture of Alice's trajectory through space-time. Now here is Bob. What is Bob's? So Bob is standing some fixed distance away from Alice, like this. So the distance between Alice and Bob don't change. And Bob has his own clock. Tick, 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 tick. How would I draw Bob's world line in Alice's space-time? Yeah.
Is Bob not moving?
Bob is not moving. He's at rest.
So like whatever x coordinate you that, just draw a vertical line up from there.
Right. So Bob initially is over here, some fixed distance away from Alice. Maybe this is 2 meters. Okay. At a later time, he's also 2 meters. At a later time, he's also 2 meters, and so on. So he remains the same distance away from Alice as time goes on. Okay. What about Bob's clock? Okay. What about when 1 second elapses for Alice, say between here and here, how much time will have elapsed for Bob? Are you sure?
Alice and Bob are both at rest.
Yeah, they're both at rest. They're at rest with respect to each other.
So then,
okay. What if I put a massive desk over there? That's not a very good picture of a desk. Let's put a dog. A massive dog along Alice's x-axis located over there. Is it still true that when 1 second elapses for Alice, 1 second elapses for Bob?
No.
How many say yes? How many say no? The correct answer is no. Okay? If you have a massive object over here, then that affects the rate at which time moves. So as we heard yesterday, Sundance told us about that light beam. So remember, he had this elevator here, and we have this light beam, which bends like this. And he said, in order to make sense of this, so this is the picture in this accelerating spaceship. According to the equivalence principle, it means that if you were standing on the surface of the Earth like this and turn on a flashlight, the beam goes out like that. The mass of the Earth will bend the beam. Okay? Gravity bends light. And since it basically has to take the same time to go from there to there as to go from there to there, and for the speed to always be the speed of light, it means that time moves more slowly down here than it does out here. Okay, so time, the rate at which time moves depends upon your location in a gravitational field. So here's the Earth. It creates this gravitational field, actually a warping of time in the neighborhood of the Earth here, such that time moves more quickly at this level than it does at this level. And you'll see a lot more of that as we go forward with these lectures. So it's not obvious that Bob's clock is going to be moving at the same rate as Alice's clock. But because there's no massive objects around, okay, it's reasonable to assume that's the case. And in fact, that is true. Okay, so what that means is when 1 second elapses for Alice, 1 second will have elapsed for Bob. But Bob's clock need not be synchronized with Alice's. For example, when Alice's clock reads 0, Bob's clock might read 7. Okay, in which case, this is what? And so on. Okay, so this is time according to Bob. The point is, when 1 second elapses for Alice, 1 second elapses for Bob, because they are at rest with respect to each other. Okay, but now here we have Cleopatra. In a space diagram, her motion is she's moving with some velocity v to the right like this. Okay? So how would I draw her world line? Diagonal. Okay? So what that means is, as time goes on, Cleo is moving to the right. Okay? So her line is going to be tilted like this. Okay? Right. And so now the question is, what is, when 1 second elapses for Alice, okay, how much time will have elapsed for Cleo? Okay, so remember here, Cleo here has her own watch. Okay, this is, I'm Cleo, and I've got a watch. My watch is ticking away. Okay, so Cleo's watch might read, say, 0 over there, and then as time goes on, it might be read 1 over there, it might read 2 over there, and so on and so forth. Okay, so how do I, when 1 second elapses for Alice, how much time elapses for Cleo? More than 1? How many say more than 1? How many say less than 1? How many say same? Okay, so it's definitely not the same, and it turns out to be less than 1. Okay, so what it looks like is something like this. This is Cleo when her clock reads 0. Cleo, when her clock reads 1, is actually maybe, say, over here. Okay, so that means as Cleo is moving like this, when her clock reads 1, she's at a certain location in Alice's space, and a certain amount of time has elapsed for Alice. Okay, so she's at a certain location in Cleo's space, and a certain amount of time has elapsed for Alice. Okay? And so more than 1 second will have elapsed for Alice. So maybe 1.5 seconds. So Alice will look at Cleo's watch and say, your watch is running slow. Okay, and we'll get to this. We will understand exactly why this slows down and so on. Okay, and similarly, if this is 1 second for Cleo, we just march up in even intervals like that. Okay? So what if we have, say, I don't know, Dogbert, who's going really, really fast to the right? How do we draw his world line? More, right. So it's also tilted, but more tilted. Okay, so it might look something like this. So that's time according to Cleo, and we'll have time according to Dogbert over here. Okay, so what about the spacing between Dogbert's, say, 0? Where would I put 1 second? Would it be further up than this? Yeah, so the effect gets more pronounced, okay, as we speed up. Okay, so now all of these motions that are happening are constant velocity. Bob is at a constant velocity of 0 with respect to Alice. Cleo is at a constant velocity v with respect to Alice, and so on. These are all uniform motion. What about non-uniform motion? What about accelerated motion? Can special relativity deal with accelerated motion? How many say special relativity is fine with accelerated motion? How many say special relativity is not fine with accelerated motion? Okay, so I hope to reverse this hands going up, okay? It turns out that special relativity has absolutely no problem with accelerated observers. And that's exactly how, in fact, Einstein, that was one of the stepping stones in getting from special relativity to general relativity, a theory of gravity, is Einstein thought about accelerated observers in the context of special relativity. So here's an accelerated observer. Okay, so this is, I don't know, Ed. And Ed goes like this. He starts at rest, and then he speeds up, and he runs to the right, and then he runs back like this. Okay, so how would I draw Ed's world line? Yeah. So you would start like this. He starts moving to the right. Okay, but then as time goes on, he eventually slows down, comes to a rest. At this point, he's momentarily at rest. When you're at rest with respect to Alice, then your world line is vertical. You're not moving in space, just time is moving. And then he picks up speed in the other direction, and then he comes back. Okay? So during this time, when he's in motion with respect to Alice, there will be funny things happening with his time. But then here, say when he's nearly at rest here, then when 1 second elapses for Alice, 1 second will elapse for Ed. Okay? So anyways, that's the basic idea of space-time diagrams, and we will talk a lot more about this as we go along, and we will actually figure out exactly this time dilation, et cetera, et cetera. Okay.